Welcome children. This is the second video on the chapter force. In this video, we will be learning couple, moment of couple and equilibrium of bodies. So let us proceed with. Let's begin with couple. A single force applied on a pivoted body alone does not cause rotation of the body. Actually, the rotation is always produced by a pair of forces. In the given examples, the rotation is due to the force externally applied and the force of reaction produced at the pivoted point. The force of reaction at the pivot is equal in magnitude but opposite in direction to the applied force. The moment of the force of reaction about the pivot is 0 because its distance from the axis of rotation is 0. So, the force of reaction at the fixed point is being shown here in the example, the diagrams. The pair of external force and the force of reaction is called couple. Few examples of couple have been shown in this slide. For example, when we open a door, the rotation of the door is produced by a couple consisting of two forces. The force which we exert at the handle of the door and an equal and opposite force of reaction at the hinge. Sometimes we require a larger turning effect than two forces, equal in magnitude and opposite in directions, are applied on the body explicitly such that both the forces turn the body in the same direction. Similarly, while turning a water tap, tightening the cap of an ink pot, turning the key in the hole of a lock, winding a clock with the key, turning the steering of a car, driving the pedals of a bicycle, etc., a pair of forces, that is, couple, is applied for rotation. Thus, two equal and opposite parallel forces not acting along the same line form a couple. A couple is always needed to produce a rotation. Next, we are going to talk about moment of couple. The figure illustrates the effect produced by a couple. AB is a bar which is pivoted at a point O. At the ends A and B, two equal and opposite forces, each of magnitude F, are applied. The perpendicular distance between the two forces is AB and it has been marked here D, which is called couple arm. The two forces cannot produce the translational motion as their resultant sum in any direction is 0. But each force has the turning effect on the bar in the same direction. Thus, the two forces together form a couple which rotates the bar about the point O. From the figure you can see the two forces rotate the bar in anticlockwise direction. When we talk about moment of force F at end A, it is given by product of force and the distance of the point of application of force from the pivot point, that is OA, and it is in anticlockwise. Same way, moment of force F at the end B is given by F into OB, and that is again in anticlockwise direction. So, the total moment of couple, that is, moment of both the forces, is given by F into OA plus F into OB, and that comes out to be F into AB. And AB has been marked here D, that is the distance between point A and B. And it comes out to be F into D, and again it is in anticlockwise direction. Thus, we can say that moment of couple is given by product of either force into perpendicular distance between the two forces, and we call it as couple arm. Hence, moment of couple is given by product of either force into couple arm. Now we are going to talk on a new concept of equilibrium of bodies. So what do you mean by equilibrium of bodies? When a number of forces acting on a body produce no change in its state of rest or of linear or rotational motion, the body is said to be in equilibrium. We have already done that when a force acts on a body, it can produce translational motion if the body is free to move, or it can produce rotational motion if the body is fixed at a point. But in certain circumstances, it is possible to apply number of forces such that the resultant of all the forces is zero. So, they do not change the state of rest or linear motion of the body. And the algebraic sum of moments of all the forces about the fixed point is zero. So, they do not change the rotational state of the body. Then, the body is said to be in equilibrium. Now, let's see the kinds of equilibrium. Kinds of equilibrium. The equilibrium is of two kinds: dynamic equilibrium and static equilibrium. So, when a body remains in the same state of motion, that is translational or rotational, under the influence of the several forces, the body is said to be in dynamic equilibrium. An example has also been quoted. For example, a train is moving with uniform velocity. So, what is static equilibrium? When a body remains in the state of rest under the influence of several forces, the body is said to be in static equilibrium. Now let's do the dissection of the two kinds of equilibrium. Let's discuss more examples of the two kinds. So in this slide, you can see few pictures that are related to static equilibrium and dynamic equilibrium. Let's discuss these one by one. In the first figure, you can see the two are sitting on the two different sides of the seesaw. So, in a seesaw, when the seesaw is balanced in horizontal position, the clockwise moment of force due to the object on its right side balances the anti-clockwise moment of force due to the weight on its left side. And the seesaw has no rotational motion. That is, it is in a state of static equilibrium. Same way, if a book is lying on a table, the weight of the book exerted on the table vertically downwards is balanced by the equal and opposite force of reaction exerted by the table on the book vertically upwards. Thus, the book is in static equilibrium. If a body lying on the tabletop is pulled by a force F to its left and by an equal force F to its right, the body does not move. The reason is that the applied forces are equal and opposite along the same line, so they balance each other. That is, there is no net horizontal force on the body. Hence, the body remains at rest. Now let's see a few examples of dynamic equilibrium. If you can see here, a raindrop reaches the earth's surface with constant velocity. The weight of the falling drop is balanced by the sum of the buoyant force and the force due to friction, that is, due to viscosity of air. Thus, the net force on the drop is zero, so it falls down with constant velocity. An aeroplane moves at a constant height when upward lift on it balances its weight downwards. From the third example, a stone tied at the end of a string, when railed in a circular path with a uniform speed, it is in dynamic equilibrium because the tension in the string provides the centripetal force required for the circular motion. Similarly, the motion of a planet around the sun or the motion of a satellite around the planet or the motion of an electron around the nucleus of an atom are in dynamic equilibrium. In each case, the force of attraction on the moving body provides the necessary centripetal force for circular motion. Now, the question arises, what are the two conditions that must be satisfied for a body to be in equilibrium? So, the answer is, first, the resultant of all the forces acting on the body should be zero. And second, the algebraic sum of moments of all the forces acting on the body about the point of rotation should be zero. That is, the sum of anticlockwise moment about the axis of rotation must be equal to the sum of the clockwise moment about the same axis. With this, we finish with the three concepts, and we promise you to bring the new concepts in the next video. So thanks for watching and wait for the next video.